In our previous video, we started completing our shadow work journal and used correlation and mutual information to become acquainted to the first insights it might reveal. However, our goal through our shadow work app is to identify the root of thought patterns which generate our emotional and cognitive barriers with a direct impact on our mental health and well-being. We aim to use ML algorithms to highlight what processes and strategies may help us shed beliefs and emotions that no longer serve us. The journaling and shadow work functionality is an exercise of self-discovery. Knowing ourselves reflects a classification rather than a regression model. As we've seen when exploring mutual information, the scale of significance column stands out as Y. X is everything else, our wounds, our needs. In our previous video, we have been working with the undated dataset which we created by dropping the date of reflection column in order to explore the correlation and mutual information. We shall therefore return to our initial dataset, DF. We can now separate the train test data. Past entries train the model. Future entries test it. To honor time, let's make a pact. All reflections you write in the next 2 weeks belong to the test set. When splitting the train and test data, we'll go for an arbitrary random state of 100 and a test size of 0.20, meaning that 20% of our data is used for testing, whereas 80% for training. Our XAI videos taught us that the random state parameter is introduced to ensure the reproducibility and consistency of random processes in machine learning. Since we need to monitor our evolution in time through the date of reflection column, we won't shuffle our dataset. In our dataset, we work with no less 29 columns. Which of them should we prioritize? Since we don't quite assess which of the features are more impactful to our evolution, I would recommend normalizing rather than standardizing our data. Before we explore what algorithms might suit us best, let's first check whether we are going to work with balanced classes. For counting values in our scale of significance column, we came across classes with below 10% support, which can pose a massive challenge. In building models, we can either drop them or fuse them. But, in a shadow work app, clarity about our inner world poses a very high stake, so we can't just overlook issues that might be important for understanding ourselves. We choose our algorithms and add a balanced class weight in them to see how they respond in these circumstances. Small data sets, which conventionally start from 1,000 rows, exaggerate imbalance problems and pose a challenge for class imbalance strategies we went through in our videos. As a frustrating reality we'll come across, the smaller the data set, the more impactful the class imbalance. Given our goals with our shadow work app, the decision tree could encourage us to excavate the impact of various events till we get to the common wound activated by our most upsetting triggers. The random forest classifier, on the other hand, could allow us to explore the same event from multiple perspectives, preventing us from taking things personally. Mimicking our brain, the MLP as a popular neural network algorithm allows us to introduce a more rational approach to things and de-amplify the intensity which we attach to various episodes. Let's go for all three of them and see how they behave. For the decision tree classifier, for which we'll go for a maximum depth of 5 branches, and the popular and arbitrary number of 42 as random state. For the random forest, will for 100 estimators and a depth of 7 branches and the same 42 random state. For the MLP, we'll go for 50 as the hidden layer sizes parameter defines the network's depth and width, which directly impacts its capacity to learn complex patterns, 500 iterations, and the same 42 random state. The balance class weight parameter tells the model, give more importance to minority classes and less to majority classes. Let's now test them and then evaluate them. We'll import the classification report and check out our result. Our accuracy is low, and some classes have precision/recall of 0. This is expected because our dataset is tiny and imbalanced. Can we make this work? I, for one, am optimistic. Next time, we'll fight imbalance with Smote/Tomek and call on Optuna to guide us with wisdom.